Okay, gonna finish out. Get my clicker here. With topics on logistic regression. I guess show of hands. Anybody worked with logistic models previously? So Sean has a little bit. Anybody else? I'm not seeing. Ignacio maybe a little bit. Okay. So basically, with the logistic regression, the same general principles apply. The only thing that we're doing now, instead of having a continuous outcome, we've got a categorical outcome. Different types of logistic models that we can run. What we're going to be working with here is a binary logistic model where we just have a dichotomous outcome, but we can extend these principles out to multichotomous outcomes, so multinomial logistic models where we've got categorical outcomes. Starts to get a little bit more complicated, but basically the stuff that we're working through here all applies to the multinomial logistic regression. So we're just going to focus on this. And again, these are nice kind of slick models. You just have to sort of be confident in how we're going through and interpreting things, just so that we're getting the most out of our information. So click there. Oops. All right. So for the models we've sort of worked up to this point, again, really through pretty much since we started in the fall, our analyses are limited to things that are involving one or more continuous outcomes, right? So our level of measurement is either continuous or we're treating it as continuous. Now, for us in psychological science, this is generally not a big deal. Most of the things that outcomes that we're looking at and working with generally involve something that exists along a continuum, even if we're saying clinical world and working with diagnoses. Diagnoses isn't like the underlying construct continues to be continuous. At some point we say, okay, here's the cut point where someone's tipped over into a diagnosis or not, but generally thinking about things along the lines of a continuum. But sometimes we're interested in behaviors, processes that do exist sort of as either as measured or as conceptualized as types of categorical variables. And when we run into this, then we're sort of run into some problems with our variance on standard regression. Standard regression might give you an approximation, but it doesn't do a good job of getting precisely at sort of the distribution of some of those outcomes. Okay. Other thing that goes on with our continuous models, it involves a lot of different assumptions about the distribution of data in a relationship between variables, right? This is probably where we spend the bulk of our time, just going through and doing screenings, trying to make sure that the data that we're trying to submit to a model adheres to the underlying assumption of that model. Otherwise, we have questions about interpretability, bias, and things like that. And as we start to get more and more sophisticated and complicated analyses, we tend to have more and more different assumptions. And sometimes we're going to run into situations where those assumptions aren't tenable anymore. The data that we've collected is real world data, and it doesn't always fit the mold. And so we may get into situations where I want to run this analysis, but the data that I have don't conform to the model to the point where it's starting to become questionable whether or not I'm going to get any interpretable results with things. Okay. And so one of the things we can do in these situations is make a transition over into some categorical models. This is just one of a whole range of categorical analyses. If you ever have an opportunity to take a spare class through stats or something like that, categorical analysis class is going to be excellent. It's kind of a different take on some stuff. Kind of one of the more basic approaches is going to be some of our logistic regression models. When we're talking about logistic regression, what we're doing is we're predicting some discrete outcome, but still based on that linear combination of our independent variables or explanatory variables. Okay, so same idea as the regression models that we've worked up with up to this time. The difference here is we've got some sort of categorical outcome. Okay. And the nice thing about our logistic models is they tend to be more flexible than other multivariate analyses. Okay, we don't have all the assumptions that come with our regression models and some of these other things that we've been working with. Within our logistic models, I don't have any assumptions regarding the distribution or level of measurement of our predictors. These analyses handle categorical predictors really well. Also, if I have explanatory variables that are really gross, have really gross distributions, it's fine. Now, if I have nice normal data, it optimizes them. They work sort of, it's nice for them to have them, but it's not an underlying assumption, right? So again, Nick, if you're looking at using number of days of alcohol use to predict some outcome, right? Number of days of alcohol use in any sample is going to have an ugly, nasty skew. And so you can go through and transform, do X, Y, and Z. But if what you're looking at is some sort of, could be conceptualized as some sort of categorical outcome, all of a sudden the nasty distribution, worrying about that goes away because we don't need to worry about it within these models. We're also not overly concerned between linearity between our predictors and our outcome because our outcome is nonlinear anyway, so we make some adjustments for that. Equality of variance, homogeneity of variance, heteroscedasticity assumptions, don't have to worry about those with our logistic models. And so we start to get into some a set of analyses that are much better at addressing some of the warts that come with real-life data, and we can start to ask some interesting questions if we're working with a categorical outcome, right? And so some examples of questions that we might address with a logistic model, if we're wanting to know, can prediction of a categorical outcome exceed chance using a linear combination of variables, okay? Basically, as with a classic regression approach, our approach with logistic regression is classification, right? I've got a set of predictors. Can the best linear combination of my predictor variables do a good job of identifying what group or category people are falling in, right? So we can look at classification types of questions. We can ask the unique relation of individual predictors with our categorical outcome. Same thing as as in regression, not depression. Regression might give you depression. You might have regression depression at this point. I just coined that. Don't steal it. I'll use it for something. We could ask, do external variables influence the magnitude and or direction of relations between specific IVs and an outcome? Chris C., what am I talking about there?
So with the external variables,
yeah,
the magnitude of the outcome.
Yeah.
Are you talking about like third variables there?
Yeah. So if I'm asking whether or not some external variable starts to impact the magnitude or direction of associations between some specific predictor and an outcome, what does that sound like I'm talking about?
The forever question of mediation or moderation. I think this one's moderation.
You're right. It's moderation, right? We got, is some external variable changing the magnitude, the nature of the association between two other things? All the things that we can do in our regression models that we've worked up to this point, we can ask the same types of questions with our logistic models, right? And then to what extent does model reliably classify individuals? This kind of gets back into not just does our model do better than chance at predicting where people are at, but can we actually use this as a good method for determining whether or not people are in certain categories and things. Yeah. Questions on kind of the basics, the rundown of these logistic models here. Okay. All right. Come on now. Oh, there we go. Okay, so first thing we want to do before we get into the nuts and bolts of this, I want to do a review of odds and probabilities. Has anybody in their research up to this point done stuff with working with odds, interpreting odds ratios? Is that something that comes up in people's areas some? No? Not so much? Okay. So one of the things we want to do is make sure that we're getting things clear in terms of interpretive purposes, difference between odds, probabilities, and things along these lines. So here, in our data, we've got a, this is from Narina, I think, some data on death sentences for black versus white defendants in some sort of database or something along those lines, right? So we have racial ethnic background of candidates or sort of defendants, black versus white, and then whether or not they received a death penalty sentence, yes versus no. Okay. And so if we're talking about probabilities, we're all pretty comfortable with probabilities, right? Think about probability, calculating this as the number of outcomes we've seen over the total number possible of outcomes, right? And when we think about probability, probability being bounded from 0 to 1, 0 means it's impossible, 1 means it's an absolute certainty, some decimal in between there showing that sort of varying levels of probability. So for these data, the probability of execution is about 8% or 0.08. Alicia, how did I calculate that?
The number of outcomes divided by the number of possible outcomes.
Yeah, and where am I getting 0.08?
So the 33 divided by the 825.
Okay, so close. How many?
33 by 284.
Okay, well, if we're talking about the probability of execution for the sample as a whole, what are we calculating there?
So the 825.
So what over 825?
The 284. No, the 33.
How many total executions do we have in this set?
Oh, sorry, 66.
66. 66 be divided by 825, right? So in this sample, 66 people received a death sentence. 825 people in the set, right? And this will give us a probability of execution overall of 0.08. Okay. Now, if we were looking at probability of execution for black defendants, is 0.12 or about 12%. How did I calculate that, Alicia?
That would be just the 33
divided by
the 825.
Okay, if I'm just talking about how many black defendants do I have?
284.
Okay, so how did I get the probability of 0.12?
The 284.
So if I'm calculating probability of execution for black defendants.
The 33 by 284.
There we go. 33 divided by 284. Okay, so probabilities, pretty straightforward. We talk about these in terms of percentages, right? There's a 12% chance that of execution for a black defendant, 8% chance of execution for everybody in the set, right? Comfortable with probabilities. Everybody comfortable with probabilities? Questions about probabilities? We like probabilities.
I don't understand betting, but I feel like that, like, I don't understand what a parlay is. People say that word and I don't know what it means.
Okay, well, we'll talk later. Like Chris M's in trouble with his bookie, and so now this is a different type of situation. Probably need to understand this before you get in too deep, but yeah. So basic probabilities. We like probabilities. Easy to go through and kind of talk about this. Where people start to get in trouble with their loan shark is when they don't understand odds ratios. Okay, this is going to be a situation. Odds are going to be different. Odds are going to involve the occurrence of A divided by the non-occurrence of A. That's going to be our odds. And then if we take one odds over another odds, this is where we get into odds ratios. Okay, now odds are different than probabilities in that odds can exceed a value of 1. Odds are bounded by go from 0 to infinity. You can't have negative odds, but start at 0, often to infinity, as opposed to our probabilities that are bounded by 0 and 1. Okay, and so if we're looking at these data here, who do I want to pick on? CJ, if I'm looking at this table here, I'm saying the odds of execution for a black defendant is 0.13. How did I get that?
Let's see. Is that 33 divided by 251 over 33 divided by 508?
Okay, so jumped a little bit ahead. If I'm just talking about the odds of execution for a black defendant, what's all I need to calculate there? I'm just talking about black defendants.
Just the 33 by 251.
Yep, that's it, right? So again, my odds are, this is the odds of death sentence versus not death sentence, right? So different than our probability, which is the or sort of the number over the total. Odds are working with occurrence over the top of non-occurrence. Okay, and so if I'm looking at the odds of execution for a white defendant, right? Again, CJ is 0.06. How did I get that?
33 divided by 508.
33 divided by 508, right? So I've got an odds of execution for black defendants as 0.13, odds of execution for white defendants 0.06, right? So they're different than the probabilities that we calculated. But what we can also do is if we take the odds of execution for a black defendant and divide that by the odds of execution for a white defendant, what we then get is an odds ratio. And so here, tomorrow, we find we got an odds ratio for the execution of a black defendant relative to a white defendant is 2.02. How did we get that?
0.13 over 0.06.
Yeah, right. So we have the odds of execution for a black defendant divided by the odds of execution for a white defendant, which gives us our odds ratio, right? So odds ratios are a little bit confusing because it's a ratio of a ratio. But what we want to do is be very clear in terms of how we're going through and interpreting these. If you're good and can go through and interpret odds and odds ratios appropriately, they contain a lot of they contain a lot of information. So if I'm going through and thinking, so it's once I sort of get the system, it's okay and easy to go through and interpret and sort of calculate these. But the interpretation starts to get tricky. So if I have the odds of execution for a black defendant is 0.13. What I can say and interpret this is I can say the likelihood of execution among black defendants is 0.13 times that of non-execution. So tomorrow, does that mean that execution is likely among black defendants?
Is it likely?
Yeah.
Yes.
Well, if the likelihood of execution is 0.13 times that of non-execution, in an objective standpoint, is that a likely outcome? No. Okay, right? And so if we go through and we look at those odds, right, we see that of the 284 cases, only 33 individuals received the death penalty, right? So objectively, this is not a likely outcome, right? Again, when we see odds that are less than 1, that suggests that something is less likely. Odds that are greater than 1 suggest that it's more likely than the alternative. Odds exactly at 1. Ignacio, what if I have an odds of 1? What does that mean? Not 100%. So if I have an odds of 1.
It's the same. Sorry.
Yep. It's the same. It's 50-50. It's a wash, right? The likelihood of the event is equally as likely as the non-occurrence of that event, right? So here, when we have an odds of 0.13, that suggests that we have something that's actually relatively unlikely within the context of sort of events versus non-events here, okay? But oftentimes, odds less than 1 can be a little bit more difficult to kind of wrap our head around. But what we can do is we can flip this around, right? What we decide is that our event or our non-event is kind of arbitrary. I could alternatively say that execution here 87% less likely than non-execution for black defendants, right? So if I take that odds of 0.13 and I subtract it from 1 being neutral, right? Kind of puts it in terms that's a little easier to talk about and understand, right? So if I say the likelihood of execution among black defendants is 0.13 times that of non-execution. Who sort of immediately understands that as sort of a meaningful metric? Yeah, me neither, right? But if we just take that and kind of manipulate that around, and I say execution is 87% less likely than non-execution, who does that ring a bell for, right? It's just more intuitive in terms of understanding kind of what's happening, okay? So do people see how we can kind of go through and flip this around? We could also turn this around. We could say that the likelihood of non-execution for black defendants is 7.6 times that of execution, right? So here, our event is just a no or a not death penalty verdict versus a death penalty verdict. If we just flip it around, now we've got an odds of 7.6 instead of 0.13, right? And so we can just turn that around. People see how we're playing with these odds ratios a little bit? Okay, so this is just looking at the odds of a death penalty sentence for a black defendant. But maybe what we would want to do is we want to compare that against some other group, right? Some other reference group. And this is where our odds ratios start to come into play and can start to be very, very informative. So if I just look at the odds of execution for a black defendant is 0.13. Siley, do I think that that's a whole lot?
No.
Probably not, right? And then what if I say, hey, the odds of execution for a white defendant are 0.06? Is that a lot?
Yes. Or no?
No, that's still pretty rare, right? But what I can start to do is compare these two. If I can create an odds ratio, it starts to sort of give me some sort of comparison here. So again, if my odds ratio of execution for a black defendant relative to a white defendant is 2.02, what I can do is I can interpret that odds ratio is I can say, so with an odds ratio of about 2, I can say the likelihood of execution for a black defendant is approximately twice that observed for white defendants. Siley, does that seem problematic?
Yes.
Yeah, that seems problematic, right? Individually, the likelihood of death sentence is pretty low, right, for both groups. But if I compare the two, it looks like the odds of death sentence are twice that of the odds of a white defendant, right? And again, just playing around with how we're interpreting these, I could take that odds ratio of 2.02, and I could say odds of execution are approximately 100% greater for black defendants versus white defendants. Nick, where did I get that 100% from?
Division.
Actually, not in this case, not division.
Multiplication. I don't know. You divided it by, I don't know.
Okay. If the odds of execution for black defendants were equal to white defendants, what would my odds ratio be?
0? Or what? It'd be 1.
It'd be 1, right? So again, when we're talking about odds, 1 always is neutral. 1 is neutral odds. This is probably where Chris M got in trouble with his bookies, right?
What's 15 to 1? What's 15 to 7?
Right. So it all gets really confusing, right? 1 means even money. 1, odds of 1, so it's a toss-up, right? And so within the context of this, if the odds of execution for a black defendant relative to white defendant were even, if it were happening at about the same rates, we'd expect an odds ratio of 1, right? And so what we can do with that odds ratio, we can take our odds ratio and subtract 1 from it. So Nick hit on most of our choices outside of subtraction, but if we take 2.02 and subtract 1 from that, that's going to give me the percentage likelihood greater for this odds ratio, right? So what I did here is I took that 2.02 and I subtracted 1, which gives me 1.02. So I could technically, odds of execution based on these data are 102% greater for black versus white defendants. Okay. Yeah, Chris.
So what do you do when the total cell sizes are unbalanced?
That's actually not a problem with this. I mean, it can get to be a problem. And we'll talk about that later in terms of predictive utility in your model. but the unbalanced cells aren't a problem necessarily in and of themselves, because if we're trying to predict something, a lot of times with the things that we're trying to predict with these models are sometimes relatively rare things. Now, if they're super rare, it starts to limit our predictive ability, but unless cells start to get really small, we're generally okay with this. Okay. Other questions? Okay. So, quick review. So these categorical analyses look similar to, and with these type of data, we could easily look at this with a 2x2 chi-square test of independence. Show of hands, keep them up, because I don't have all of you on video. Anybody sort of do work with chi-square regularly within their stuff? Not a lot of chi-square. Yeah, I don't do a lot of chi-square either, except for if I'm just trying to tell people that my samples don't differ on some categorical variable. This ended up being sort of CJ within experimental tradition when you're getting categorical sort of types of things. Within experimental types of stuff comes up more often. But chi-square, sort of one of our fundamental sort of basic univariate tests. And what we're looking at here is whether or not we have some sort of relation or dependence in the frequency of two different nominal variables, so two different categorical variables, okay? And so what our chi-square statistic does is it compares the frequencies that we've observed in our table relative to what we would expect under the null hypothesis, right? So going back, Chris M., to your question about unbalanced cells, sometimes things are just sort of more likely to be sort of, we're more likely to observe one thing versus another. But what our chi-square test is doing is saying across these two groups, are we seeing some sort of dependence going on? Okay. And chi-square is actually pretty easy to go through and calculate. So our chi-square statistic here is just going to be, our chi-square is equal to the sum of our observed frequency minus our expected frequency. And then we square that and we take that over our expected frequency. Okay. And within our chi-square analyses, our FO, this is our observed frequency. This is just sort of what we're observing. Our expected frequency, this is going to be our column total multiplied by our row total divided by the number of people in the design. And then our degrees of freedom are row number of rows minus 1, number of columns minus 1. Okay. So within this set, what we see, okay, is we see for our black defendants, we had 33 death sentences, 250 not. For our white defendants, 33 death sentences, 508 not, right? Now, if we just look at our death sentences, we like 33, 33. It's even Steven, right? But Chris M., who did we have more defendants? Did we have more white defendants or more black defendants?
Which Chris was it? Was it me?
Oh, Chris M. Yeah.
Okay, cool.
Was I muted?
Yeah.
Oh, there's more white people.
Yeah, there's more white people.
I thought you were looking at me like that was not right.
No. Yeah, you're muted. Yeah. So yeah, we have the same number of death sentences for our black defendants versus our white defendants. We got a whole lot more white defendants, right? Which means the frequency of death sentences in black defendants is much higher, right? And so if we go through and we use for each one of our cells, we calculate our expected frequency. So here we take our column total, which is going to be 66, times our row total, times 284, and divide that by 285. This is going to give us our expected frequency here, right? And then we do the same thing across each one of our cells. And so what our chi-square test is doing is it's looking for each one of these cells. We're taking our observed frequency, subtracting our expected frequency, squaring that, and then dividing it by our expected frequency. And then we do that for each one of our 4 cells. Okay? And if we do this, what we find, right, we've got 33 divided by, subtract 227, square that over 227, same thing through each of these. We get a chi-square statistic of 7.74. Now for 1 degree of freedom, right? So we've got degrees of freedom. We got 2 rows, -1 is 1. 2 columns, -1 is 1. Degrees of freedom equals 1. Our critical value for degrees of freedom 1 for our chi-square is 3.84. And so, Sean, what is this test telling us?
It's summing the difference between the observed and the expected.
Yeah. And so what would our conclusion be based on our chi-square test here?
So the higher the chi-squared, the more likely the null is not true.
Yeah, right. And so here, with a test statistic of 7.74 and a critical value of 3.84, we've got very strong evidence against the null hypothesis here, right? That suggests that yes, there is, based on our data, appears to be a very clear dependency between the race of our defendant and whether or not they receive a death penalty. Okay, so Chris M., going back to your question, do we need to have balanced cells? No, we often won't, right? But we're seeing, even though we have small number of cells, right, it looks like overall execution is not a common outcome, but it appears to be a much more common outcome for our black defendants as opposed to our white defendants, right? And if we go through and we take a look at just descriptively within our cells, we're seeing that execution is underrepresented among our white defendants, and it's overrepresented among our black defendants. This is how we can go through and start sort of teasing apart where that actual difference is coming up. Okay. Questions on this? People kind of seeing how this is working out? Okay. So, we've got these categorical outcomes and kind of going through and starting to understand our odds ratios and things along those lines. But what we might want to do is move beyond our simple chi-square statistics and want to go through and say, hey, I've actually got a bunch of different explanatory variables that I would like to see determines death sentences or sort of the likelihood or the probability of death sentence. We don't have anybody in our class right now who's psych and law, but if I was a psych and law person, I might say, well, defendant race probably isn't the only thing that goes in to determine whether or not someone receives a death sentence or not. I'm interested in going through and exploring some of these other variables, right? And so what we're often wanting to do within these models, particularly with the dichotomous outcome, is we're interested in calculating the probability of some event, right? What's the probability based on this information I have of this thing happening, right? The problem that we run into with our standard statistical models is our probability functions aren't linear, okay? Our probability, if I'm looking at the probability of my outcome, it's being bounded by 0 and 1, right? So it's either 0 never happens, 1 always happens. But in between there, we get this sinusoidal type of S-shaped curve, right? So here in the middle, yeah, things are jumping up, but as we start to get closer and closer to 1 and closer to 0, things kind of start to taper out, right? And as a consequence of this curvilinear function here, what we see is that the change in our expected value of y, our probability, given a unit change in x here, starts to decrease as we get closer and closer to the bounds of our scale, okay? So Tamara, if we're looking at sort of this probability graph here, does a 1 unit change in x have more or less of an impact on increasing probability in the center or at the ends?
At the ends.
Is at the what's going on at the ends here?
The probability increases.
Probability increases. Does it increase as much as it does here in the middle?
No.
Yeah, right. So if I go from 0 to 1, right, and I look at here's probability at 0 when x is at 0, and here's the probability when x is at 1, I get a 10% increase, or sort of a 10% increase in the probability, right? If I go from 3, let's call it 3 to 4, how much of an increase do I get in the probability? Just a little bit, right? And so what we see is that with this nonlinear function, the expected bang for my buck that I get with a unit change in x starts to become less and less and less as I get sort of closer and closer to those 0 and 1 points. Okay. Now, Alicia, if I'm looking at this graph, does a straight line fit what's going on here very well?
No, because you'll miss stuff on either side of it.
Perfect. That's brilliant. Yeah, absolutely. If I go through and I draw a straight line, I do okay for some of it, but at the low end, I'm overestimating. At the high end, I'm underestimating, right? And so we get into this problem. Our linear model doesn't fit the data well, right? Now we can apply a standard regression model to a dichotomous outcome. It's just not going to be super precise. It'll be ish okay, but ish okay isn't sort of what we want to have for the purposes of science, okay? And so what we see here is that our expected probability is following this logistic function, okay? And our logistic function finds that the probability of some outcome, my expected value of x given y, follows this function, right? Where I have base E taken to my linear function over the top of 1 times E, and that's I don't know, that's what that should be. I'll save this and it won't save. It'll kick it back, but note that that's what that, oops. And show that that's what that should be. Okay. So what we've got, all right, is we've got our standard linear model, right? Sean, where are we seeing our standard linear model? Where is that occurring in this transform?
Exponent of E.
Yeah, right. So we can solve for the expected value of my probability. The problem is that linear function is set in an exponent of a base C over a ratio. It's a big problem, right? And so our standard linear models don't do a good job of accounting for this. Okay. So take home message is that if I'm trying to predict a probability, I can still use a linear equation, so the same thing as we would with our regression. The problem is in order to make this work and be accurate, our linear regression model is confined to the exponent of a base C in a ratio. It's a mess, okay? And that's what makes this difficult. But what we can do, because we know that the estimation of a probability is not linear, and so what we need to do is we need to go through and transform our outcome. Okay, and if we go through and we do some basic math, if you're sort of handy with your algebra, it doesn't take you too long to see how we could go through and solve. If this is what we're trying to do, right? If we wanted to predict probability directly, this is the equation that we would need, right? But this is really hard to estimate. But what I can do is I can transform this. I can move these pieces around so that I can get this linear form on one side of the equation, right? And so what ends up happening is now this piece right here, this is just my standard linear model, right? This is just my basic regression model, right? My intercept plus predictor 1, predictor 2, predictor 3, so on and so forth, right? But what happens, again, Sean, what do we got on the left-hand side here?
You have a different link function than you normally would.
Yeah.
You just have Y there.
Yep, normally perfect. Normally I would just have Y, right? If I'm running a standard regression, I'm just predicting my expected value, my outcome straight away, right? But with our logistic models, what we're trying to do is we're trying to predict a probability, but I can't predict a probability directly. What I can predict is a log odds, right? This is the natural log of the probability of being in one group versus the probability of being in an alternative group. And so what I do, instead of, again, like in our basic linear regressions where I'm just straight up predicting sort of my expected value of my outcome, here what I'm doing is I'm using a linear model to predict the log odds of occurrence versus non-occurrence, okay? And so with this link function, there are a lot of different link functions. The one that you will see probably most common is our logit or our log odds. Sort of the thing that we're predicting, our outcome, isn't exactly what we want to predict, but we can go through and do some transformations to get back to kind of what we want to do. All right. So think about who's feeling like, okay, yeah, this makes sense. Okay, so Chris is kind of get sort of Chris C, right? If you're struggling with this a little bit, that's fine, right? And because this is kind of a difficult thing to wrap your head around. Think about it this way. Again, I'm going back to Nick because Nick is the only person sort of that I know studies things that don't have a nice and natural distribution of things on the back end, right? But if Nick is trying to predict, and his outcome is drinks per month or something like that. Nick, what is drinks per month? How is that distributed?
Positively skewed.
Positively skewed, and sometimes pretty. And if I'm looking at some other substance, if I was looking at maybe like cocaine use or sort of methamphetamine use or something like that, even more skewed, right? And so tomorrow, if I have an outcome that is super skewed, what might I do to go through and predict and sort of to fix that? A transformation, right? And so with that transformation, if Nick's interested in looking at methamphetamine use and you're a statistical consultant and you say, hey, this is really skewed and what you should probably do is transform that, right? When Nick does that, is he predicting daily use in methamphetamine? Exactly, right? So Nick's not really predicting exactly what he wants to do. He's predicting a transform variable, which works in terms of estimating things, but he might be not predicting monthly use. He's predicting the log transform of monthly use, right? Which works well for the model. But if you want to go back through and actually get at actual predicted values, what you need to back transform that, right? That's all that's happening in these logistic models. The thing that I want to predict isn't linear and so it doesn't sort of play well, and so I can predict it with a standard sort of what we would think about as our linear model. It's just the thing that I'm predicting then is no longer probability. It's this log odds thing, which is nice because log odds range from negative to infinity, just like any other continuous variable that we would want to do, and so it fits our linear model a bit better. Okay. Does that make some sense to people? Kind of, at least starting to sort of click in a little bit. Okay, so what we're going to do then is, because our logit is linear in its parameters, okay, the log odds works. Log odds is a nice continuous variable ranging from negative infinity to infinity, and if we have a nice continuous variable, then we can just use our regular old model, right? And so what our logit is going to be doing is it's going to determine the odds of being in one category versus another category given a set of predictors. And so again, similar to our standard regression models, just a little bit different where our linear regression, we're predicting expected values directly, right? If I can just plug in, values for my predictors, and then I get it and I calculate that out in my regression equation. I get my expected value, my outcome. With our logit or with our logistic models, we can do the same thing, but instead I don't get my probability. I get a log odds, which I can then go through and translate to get odds of occurrence versus not occurrence for one group versus another. Okay. Questions? All right. Run through maximum likelihood estimation real quick, just before we go on break here. So when we're going through and we're running our coefficients for our logistic regression, a little bit different strategy than what we would do with our OLS regression. Okay, there we're using ordinary least squares. Within our logistic models, we're using a maximum likelihood estimator. Now, you all read a little bit about maximum likelihood estimators before in the problem set 3. Okay, but what we can think about in terms of, you don't have to get into the nuts and bolts of all of maximum likelihood, but it's different than OLS. OLS is estimating things directly, right? There's a formula for OLS. With maximum likelihood, what we've got is an iterative estimator, okay? And so what we do with maximum likelihood is we say, okay, we have these data, right? And what maximum likelihood will do is it'll start with a set of some sort of generally random coefficients to use to estimate for the model. So when you think about this in your output, right, all your values for your coefficients, with a maximum, with OLS, those are all calculated directly from matrix algebra from your data, right? Maximum likelihood is a little bit different. What maximum likelihood is going to do is it's going to start with some random set of starting variables or starting coefficients, and it's going to plug those into the model. And then it's going to estimate that model, and it's going to see how good the model fits. Chris M., is that model going to fit real well?
Yeah.
No, it's not. Yeah. And so what that model is going to do is it's going to find sort of where it's not fitting, and then it's going to get a new set of estimators. Like, okay, how about this, right? And then are those values going to be very good? Going to be better, but probably not great, right? And so what it does is the estimator keeps doing this again and again and again and again and again until it hits a point of convergence. Convergence means that sort of further fooling around and tweaking these coefficients is sort of just producing sort of minor changes in the model, and then we would say that we've converged, right? And so what we do is that with this iterative process, in the nuts and bolts of the system, it's starting out with a random set of values, going through and running those through until the model gets to the best approximation of the actual observed data that we have, and then we say that it's converged and say this is as good as we've got, right? And so the goal of our maximum likely estimator is to get parameters that maximize the probability of obtaining the scores that we've seen in our data, okay? It's building us a model that says, hey, with these parameters, this gives us the best likelihood of getting what you're actually saying in the set that you've collected. So this can be kind of hard to kind of wrap your head around, right? But let's say, Siley, like that, like I'm seeing like just like the top of, like I'm seeing like Chris C's eyes, right? He's like almost like the sort of the version of like sort of being sort of out of camera, like it's like the virtual version of not making eye contact, right? But Siley, I'll wait for just a super hard question to go through and ask Chris. Siley, if I'm going through it and looking at this equation here, so I've got x2 plus y1 equals 9, okay? Tell me what x and y are.
They're the continuous variables?
Yeah. What values can I plug in for x that make this statement true? Okay.
And then 3.
3 and 3, right? That would give us 3 is 6 plus 3. Yep, 3 and 3 would work. Ignacio, anything else that might work for that?
I think there could be an infinite number of combinations.
You are right. There is an exactly infinite number of combinations, right? For any x, I could put any value of x into this, right? If I choose, I can choose whatever value of x I want. But once I then, Ignacio, once I choose x, what's my degrees of freedom for selecting y? 1, yeah. I can choose, I have an infinite number of possibilities in selecting for x. But as soon as I select for x, then y is fixed, right? Alternatively, I could select an infinite number of values for y. But as soon as I do that, then my x's are fixed, right? But there is no unique solution for this system of equations, right? It can be whatever I like, right? But if I start to add in another equation, right? Now all of a sudden, CJ, what values can I pick for x and y?
You could do 8. All right. 6 and 0.
Okay, so if I put 6 and 0 in, right? If I put 6...
classic. 6 and 2.
6 and 2, okay. And so that solves this. What if I throw 6 and 2 into here? So that's 12 and 2 is 2, that's 14. Does that fit up here?
Nope.
Nope, right? All of a sudden, we've got some constraints on what we can be. If we're just working with this parameter, it can be anything, right? There's no unique solution for this. But as soon as I have a set of parameters that have to be inputted to make both of those things true, now all of a sudden I have some constraints on my model, right? Now, in this case here, right, if I go through and I say, what do we got? We got x2 plus y1 equals 9, and x3 minus y1 equals 16. Okay. Now I can go through and I can solve for this system of equations, right? I can just add these and say this is 5x equals 25, okay? And Ignacio, what does x have to be now? 5, right? And what does y then have to be?
Y is 510 plus y equals 9 is minus 1.
-1, okay. So here with these two equations, right, I now have a set of parameters that perfectly make this, so that are a perfect fit for these data. Now the thing is, within maximum likelihood estimation, is there a set of parameters, Alicia, is there a set of parameters for any model that's 100% going to make sure that I perfectly predict my outcome in all cases? No, right? And so this is where maximum likelihood kind of does a version of this, but what we end up with are parameters that are kind of close enough, and kind of they're the best thing that get as closest to the possibility of us observing the data that we're seeing in our output or in our set relative to other things that we could get, right? And so what we see with this iterative process is we start to get convergence there. Okay, and so this system starts to become important. So this is what's going on when we're estimating our logistic models, as opposed to OLS, where we're calculating things directly with our ordinary least squares estimates, or estimated directly based on formula within matrix algebra. Maximum likelihood and similar estimation techniques use this iterative approach, where we start with just random values and just get closer and closer and closer as we move forward. Questions? All right, cool. So what we're going to do was jump back in with kind of a sort of a walkthrough of an example here. But let's go through and take a break, and when we come back, we'll jump back into logistic stuff. Sound good? Cool. Awesome. Cool. All right. So let's go through and talk about an example of kind of using some like sample data or something that's a kind of a conceptual example. So again, if we're talking about our binary logistic models, right, our outcome takes one of two values, 0 or 1. Okay, it's either not there or it's there. And so what we're doing with our model is we're predicting the odds of falling into some criterion category relative to a reference category, okay, based on the best linear combination of our independent variables. And this starts to become important, crucial to understand what level of our categorical outcome or any other categorical predictors is set as the reference group. Anytime you're working with these logistic models, always have to be very clear in terms of what your reference group is, because it's going to have a huge impact on your interpretations. Okay, so let's say we've got some data here. Any skiers or snowboarders in the house? No, CJ, Chris M, Nick. Okay, Siley, no skiing? You're not a hardcore out with the snow machines in Las Vegas? No. Okay, well, That was a miss. My expectations were off. I had a residual there, right? All right, so let's consider a situation where a small set of data, and what we want to know is we want to know whether or not someone falls, okay? And we're modeling falling, yes or no, as a function of trail difficulty and, say, season, okay? So we see in our data set, we've got 15 individuals on some run, and we're noting whether or not they've fallen, yes or no, right? We've got a fall, no fall, no fall, no fall. And what we're doing is we're predicting falls based on difficulty of the run, 1 least difficult to 3 to most difficult, and then season 1, 2, 3, autumn, winter, spring. Okay, and in this situation, what we've got, we've got a asterisk here. Spring is going to be our reference group. Okay, so our estimated model. This is what we're getting in our logistic regression. What we're doing, Nick, can I predict with a standard linear model? Can I predict probability directly? Nope, I can't. But what I can do is I can predict the log odds, right? And so my outcome, I'm going to get the expected log odds of falling versus not falling based on trail difficulty, season 1 and season 2, where I guess we're treating difficulty as a continuous variable, roughly, and then season as a categorical variable, right? So season 1 is going to be autumn versus spring. Season 2 is going to be winter versus spring, okay? And what we have here then is a set of coefficients that look very similar to all the coefficients that we've worked with before, right? We've got our intercept. We've got a coefficient for difficulty. We've got a coefficient for season, for our season 1 dummy and our season 2 dummy. Okay, and Sean, if I'm looking at my intercept here, what's my intercept here represent?
It's the predictor associated with spring and no difficulty.
Yeah, right. So specifically, this is going to be our expected log odds of falling versus not falling for spring with 0 difficulty, which doesn't fall on the list, right? So again, sort of starting to get into seeing how our interpretive qualities start to become important as we're going through and doing this, right? But again, what we've done is we've got the same type of interpretation here as before. It's just what we're predicting is a log odds as opposed to an actual probability or an outcome. Okay, people see what we've got, how this is working. Okay, so, but then maybe Ignacio's here, and Ignacio's not interested in log odds. What Ignacio wants to do is, Ignacio wants an actual probability, right? He wants to know, based on my model, what's the probability of falling for participant number 8 here, right? Who actually did fall and has the most difficult trail and is skiing in autumn, right? And what Ignacio wants to know is, for this individual, what the model estimated probability of falling is, okay? Now, we don't get that directly from our model, but what we can do is we can go through and plug in, we can restructure this equation to actually get an actual probability value, right? Remember now that with our logistic models, so we're predicting log odds, but that's just because we retransform that to get something that was linear in its parameters. What we can do is we can take our regression equation here, and we can take base E to whatever the result of that regression equation is over the top of 1 plus base E to this thing. And with this equation, now I can start plugging in values for difficulty and season. And if I do that, I'm going to get a estimated probability. Okay, so my model, as I estimate it, gives me log odds, but I can still restructure that equation to go through and plug in and actually get, for an individual, get an estimated probability of falling for that person with some restructuring of this equation. Okay, people see how I did that? And again, we just got our standard linear equation like we always do. It's just going in the exponent of that. So we're going to take base e to whatever sort of that number is once we run that out over 1 plus base e to the same number, and that's going to give us our expected probability. You don't see this a lot. People don't often present these as wanting to predict the exact probability of falling or not falling for, or the probability of falling for one single individual. But we also don't see people reporting expected values of y for everybody in the set either, right? We can do it, and mathematically we can get it. We just don't see it a whole lot. Okay. So what we also start to get into with our logistic models is this idea of model fit. Remember that the purpose of our maximum likelihood is to try and get a set of parameters that sort of give us a set of data that as close as it can represents what we actually found, right? So we've got model implied data versus the actual observed data, and what we're wanting to do is see so how much of a misfit that we have here. And so what we do is we can estimate the model fit in an absolute sense by calculating a log likelihood, okay? And this log likelihood is going to be equal to my value of y for an individual times the natural log of the expected outcome plus 1 minus the outcome times the natural log of 1 expected the outcome, okay? And this is our log likelihood function. If we run this out, this is what this looks like, okay? So here we have our outcome. This is whether or not people fell or not, okay? Here's our expected probability for everybody in the set. Did they fall or not, okay? And then what we can do is we can take 1 minus that probability, gives us 1 minus y hat. Then we can take y times the natural log of y hat, 1 minus y times the natural log of y hat, and then we get our log likelihood value here. Okay, so if we take a look at person 1, all right, Alicia, for our first person in this set, did this person fall?
Yes.
Yes, they did fall. And if this is my expected probability based on my model, whether or not they fell, right? So my model says that based on the parameters, this person has an 89.9% chance of falling. Did my model do a good job of capturing that person?
Yes.
Yeah, they did a pretty good job here, right? And so what we see is my log likelihood value is quite small, okay? Chris C, here we've got someone who did in fact fall. How good was my model in predicting whether or not they fell?
It's kind of tough to say because, I mean, technically, if you're talking binary coin flip, like, technically it was correct, but it wasn't very confident that the person would fall.
Yeah. If you ask me, if you're asking me like, hey, what's the likelihood of CJ winning this this game that we're playing, and I say about 50-50, is that helpful? No, it's not helpful, right?
Also incorrect.
It's 100% chance of winning that game.
Basically, a coin flip is kind of zero garb. Like it's not helpful at all. Yeah, I don't know. Maybe yes, maybe no, right? So like joke around back. Oh, is this thing going to happen? Like I gave it a 50-50 shot. It'll happen or it won't. It's like 1 to 2, right? It's not helpful. It's not predictive, right? And so as a consequence, Chrissy, what's my this would be a case that I didn't do a good job of accounting for. What's my negative log likelihood here?
It's worse than...
It's worse, right? It's considerably lower, right? And so what we can do is we can run through each and every person in our set and look at the expected probability and then sort of look at natural log and sort of get a negative log likelihood or a log likelihood for each one of these. And so what I can do is then sum up that the log likelihood. Think about this log likelihood as a residual for everybody in your set, right? And if I go through and I add these up, I get a log likelihood value here. And what I can do if I take that some of those log likelihoods and I multiply those by -2, what it does is it turns out it places that log likelihood sum on a general chi-square distribution, okay? With the lower the -2 log likelihood, the better the model fit. All right. And so what I can do then is now I've got a measure of model fit that falls along a chi-square. And if I've got a statistic that falls along a known distribution, now all of a sudden I can go through and start running tests. Okay. And so what's nice is I can start comparing models directly by subtracting the -2 log likelihood against nested models, right? So Chris M., let's say that you have in this model that you've looked at a model that includes trail difficulty and sort of season, right, as predicting whether or not someone's going to fall. Do you ski, snowboard, anything like that? Okay, you ski. What other things might be relevant to knowing whether or not someone's going to fall on any given run?
General ability.
Okay, so let's say we've got a measure of athletic ability. What else?
Amount of time spent skiing.
Perfect. Exactly what I was going to say, right? So maybe I've got a model where I think these two variables are going to improve my my overall model, right? So what I might do is I might run a model that includes trail difficulty and season as predictors. And then I run another model that has trail difficulty, season, along with years experience and general athletic ability, right? And those are nested models. And what I could do is I could go through and I could take a look at the -2 log likelihood for my model with just the two predictors, and my model with my negative log likelihood of the four predictors. And what I could do is I could go through and compare those two to see whether or not the addition of those two additional predictors improve the overall fit of my model. Does adding these into the model, does that help? Does it give me a better model? And if I've got good predictors, what should that do to my -2 log likelihood, Chris?
Lower it.
It should make it lower, right? But if I don't, right, then it's going to be roughly the same. Or anytime I throw stuff in, it's probably going to make it incrementally better. But what I can do is test this on a chi-square difference test, where I take the -2 log likelihood, subtract the other -2 log likelihood, look at the difference, and then the degrees of freedom for that difference test is going to be sort of the difference in the number of predictors across these two things. Okay, so some cool stuff with some different tests that we could do to look at the extent of whether or not my predictors are adding and improving the overall model. Questions on this? Okay, cool. So when we get our output, one of the things we can look at, and is often interesting, is go through and take a look at our classification table. Okay, and our classification table is going to tell us how good we did in terms of actually predicting sort of our outcome. Okay, so our -2 log likelihood gives us a statistical test, but just from a qualitative standpoint, I can look at my classification table and see sort of, did I do an okay job with this, right? And so based on my outcome, so here, if this is a classification table for this example that we've gone through, right? And my cut value is 0.5. So depending on whether or not, if I'm 0.5 or if I tip over 0.5, I'm going to say, yep, it's a fall. If I'm less, I'm going to say no fall, right? And it looks like, based on my results here, my model is about 80% accurate. Okay, so this is predicted. Did I predict a no fall? Did I predict a fall? This is what I actually observed: no fall, fall. So we've got 4 people who didn't fall that my model got right. I've got 8 people who did fall that my model got right. And this was someone who didn't fall, but my model predicted it was. This is someone who did fall, my model predicted it didn't. Okay, so if we think about this, these two in the diagonal, these are correct responses, right? This is a true negative. This is a true positive. Here, this is what we would call a false positive. CJ, why are we calling this false positive?
Calling it a false positive because you found something, but there's actually nothing really there.
Yep, I predicted a fall when that person didn't fall. Same thing here, calling this a false negative because
you predicted just the prediction in the observed was off.
Right. In what direction here?
You predicted that there wouldn't be a fall, and there was.
Yeah, right. So these in this, I think these are misses, these are hits, right? And what we can do is we can start to do from a psychometric standpoint, and this gets into epidemiology and things like that, and some psychometric things, start to calculate some different ways of going through and thinking about accuracy in terms of prediction, right? So one thing I can do, so overall, my model, I was 80% right? And so this looks pretty good, right? And I might feel pretty good. How do people feel about 80% right? Feel pretty good about it. I would feel pretty good about 80% right? But Chris M., this is what happens sometimes when we get into something that's very, very rare occurrence, right? If I'm if you remember back to last semester, right, when we were talking about problems with fundamental assumption or the fundamental process of hypothesis testing, right, when we're trying to diagnose schizophrenia, right? If we've got something that occurs in less than 1% of the population, how do I construct a really, really, really accurate test in terms of overall prediction rates? Yeah, well, I can just have a test that says no one has schizophrenia, and I'm going to be right 99% of the time, right? But is that a useful test? No, it's not, right? And so what we want to do, particularly if we're running with things that don't have real good base rates, starting to run some of these alternative calculations to start to try and get a better sense of the utility of our model. So what I could do is I could calculate sensitivity. This is the ability of my model to correctly identify a criterion, okay? So of all the falls, how many of those falls did we capture, okay? So how many falls total did we have in this set? 9. Had 9 falls. We got 8 of them. That's pretty good, right? And so we would say that these data have some pretty good sensitivity, right? And so what percentage of the true criterion were identified by the test? But we also have the inverse, right? Our specificity, our ability of our model to correctly identify non-criterion, right? Here we're going to take our true negatives, which are going to be 4, divided by our true negatives times our false positives. So we're going to take true negative plus true negative, my false positives, are going to be this right here, right? And what my specificity is going to do is going to tell me what percentage of non-criterion were identified as actual non-criterion, right? So in my test of schizophrenia, and my test of schizophrenia, you take this test of schizophrenia, and my test of schizophrenia says you don't have schizophrenia. What's the specificity of my model? Is it good or bad? So if what percentage of non-criterion cases were identified as non-criterion? So my test says no one is met criteria, and I was right 99% of the time. So is my specificity good?
Yes.
My specificity is awesome, right? The specificity of my test where I just say no one has it is excellent because I got 100% of the people who didn't have it. I identified them all. But what's my sensitivity look like?
Not good.
Yeah, it's garbage, right? And so this starts to get into the problem with really unbalanced designs. We start to see a large discrepancy between our sensitivity and our specificity. Okay. We can also look at our positive predicted value. This is the percentage of cases identified as a criterion by the model that actually are criterion. Okay, this is saying how confident are we that the criterion is correct? And this is a little bit different, right? So it's kind of sounds like sensitivity, but sensitivity is sort of difference in the denominator. Denominator or sensitivity says of all the people, of all the COVID cases, how many of my tests, how many did my tests detect, right? And if my test just says everybody has COVID, my sensitivity is awesome, right? Because I captured all of them, right? But my positive predictive value is going to be really poor because what it's looking at is of the cases that I had identified as positive, how many of them actually were positive. Same thing, negative predictive value percentage of cases identified as non-criterion by the model that actually are, right? So if my test said that they're not, that these individuals didn't fall, how accurate am I, right? And again, how confident are we that the non-criterion is actually non-criterion? So when we're going through, and if we go through up in the top here, we've got, looks like our sensitivity and negative positive predictive value, negative predictive value are all pretty good. Our specificity looks like it's the worst. Essentially what we've done is we've over-identified falls, it looks like that. And so we're not so good at, we're much better at predicting falls than we are predicting not falls, or capturing falls than not falls within this set. If you're using categorical models, it's very, very helpful if you can sort of sit down and sort of start wrapping your head around this, starting to think about what does this mean for the utility of my test. Okay, I went through in our lab, we went through and did a project last year looking at the extent to which checklists of trauma predict like interview-based trauma. And so we, in my field, if we want to know whether or not people have experienced a potentially traumatic event, we often have them go down through and just check off stuff, but there's obviously problems with that. And so went through with that study and actually went through and carefully teased apart in our terms of our analyses, talking about the sensitivity, specificity, positive and negative predictive value of this test. It actually turned out, I think, well. I'll post that if anybody's interested in or has ideas about stuff, what that might look like. Okay. Questions about any of this? Okay, cool. So here are just some different conceptual interpretations of sensitivity, specificity, positive, negative predictive value. Go through, take a look at those. Again, if you're working with models where your goal is to identify people who are falling into a sort of different category, this can be a really nice way to start to provide some context and interpretation around things. All right, so up to this point, we've been talking about just tests of the overall model, right? And tomorrow, what would be the analog of our test of our overall model for our regression models that we've been working on with up to this point?
Like our omnibus test?
Yeah, our omnibus test. And what's our omnibus test with our standard regression models? Our F, and our F is our test of what?
Change
The
model, like how much we predicted.
Yeah, and so what do we call that in our standard regression? Our proportion of total variability accounted for.
I'm not sure like what you're asking.
Okay, so what's our omnibus test for our standard regression model? Or like how do we determine whether or not we've got a really good model or a model that's sort of maybe not so good? What's the statistic we're looking at there?
Our R squared.
There we go, R squared, right? And so to this point, with the -2 log, like with our, and we'll talk about this, with our logistic models, we don't have a good analog of R squared. I mean, we've got model fit, but it's not super interpretive. It doesn't have a whole lot of interpretive value. It depends on how many people we have in our sample and a lot of other things, right? And so I can't just look at a -2 log likelihood and make a determination on whether or not it's good or not, right? R squared is kind of nice. There's been some efforts to develop pseudo R squareds for logistic models, but they're not that great. But to this point, when we're talking about model fit, that's kind of the stuff that we're looking at, right? But for our type of work that we're doing, we're more often interested in looking at individual predictors, right? In our regression model, what we do is we just go down through and we look at our individual coefficients, and we sort of make an interpretation based on our t-test for our individual coefficients and interpret that as evidence against the null hypotheses of no unique relation of any of those relative to our outcome, right? With logistic models, things get a little bit more tricky because we actually have a number of different ways that we can test our individual predictors. And sometimes these things don't always line up perfectly well. So what you'll see in terms of your regression table with a logistic model that we see with our standard equipment, what we get is a walled test. We call this a walled statistic. And what it is it takes our coefficient divided by our standard error and just calculates this as a statistic distributed along a chi-squared distribution with 1 degree of freedom. Okay. Similar to what we would do with our linear regression, right, where we take our coefficient, our unstandardized coefficient, and we divide it by the standard error, which puts that that on a what distribution, Nick?
Sorry, can you say that again?
Yeah, so if I'm looking at multiple regression and I have my unstandardized coefficient and my standard error, right? And if I take my unstandardized coefficient, divide it by my standard error, that gives me what type of statistic? A t, right? It gives me a t with whatever the degrees of freedom are in my error, right? Logistic, same type of thing. We just take our unstandardized coefficient and divide it by our standard and square that, take it over the standard error, square that, and that give that as a distribution on a chi-square test. The problem is calculation of our walled standard errors are inefficient, right? Does anybody remember what inefficient means in terms of our test? It means
it's not good.
Yeah, right. It means if we have a as our samples get bigger and bigger and bigger, what should we expect happen to our error? Or the bit of our prediction should get smaller, right? And these walled tests don't do that. Distribution is also imprecise. Same thing as with our Sabel test. We say, oh, we've got this test statistic that falls along this distribution. Well, kind of really, it's not a perfect match on this from a theory-based standpoint. And so what we see is that in simulation research, these walled statistics that you'll get in your output shows evidence of elevated type 2 error. Okay. Chris M., what does elevated type 2 error mean?
Your likelihood of falsely rejecting the null increases. No, accepting the null.
Okay, yeah. I was yeah. Well, and we never accept the null, but we fail to reject the null. Right? Yeah. So basically, something's there, and our test just isn't picking it up, right? And so as a consequence of this, what we know is that our test statistics for our coefficients that we get from our binary logistic models that are based on this walled test, if I've got something that's kind of on the edge, right, it starts to increase, it adds ambiguity. Now, if I've got something that's clearly sort of clear evidence against the null, that's fine. And if we're something that's sort of questionable, I would probably argue that there's a level of uncertainty there that I probably shouldn't be too worried about the walled statistic. If it's that ambiguous, there's probably not super clear that we have anything to begin with. But what we will find is that we're sort of less sensitive to than some other approaches. Okay, so this is the standard, and this is what you usually see reported, but there are problems with interpretation of those walled statistics. So what we can do instead is you can look at log likelihood difference. And this is similar to what we had talked about before. So what I can do is I can go through and run a test that has all of my predictors except for the one I'm interested in, and look at the log likelihood of the model that has without the predictor, and then compare the log likelihood of the model with the predictor, and then run a log likelihood test for the difference in those models to see if that individual predictor contributes to the performance of the model. Okay. Now, this difference in the -2 log likelihood, this is a preferred method for evaluating the unique contribution of a predictor, but is not what's given in your standard output. Okay, so if we want to get super precise, this -2, this log likelihood difference, but it's going to take a little bit more effort sort of in standard SPSS, because basically what we have to do is we run a model with the predictor and without it and look to see at the difference there. Okay, we also have a different approach, Lagrange multiplier. This is just an alternative estimate with the inclusion exclusion. It kind of falls between the Wald and the log likelihood difference. So if you've got clear evidence of effect, your Wald statistic is probably fine. This is what you're going to get in your output, but just know that they're unlike our ordinary least squares regression models. There's some differences that we can see here in terms of how we go through and test the unique contribution of our individual predictors. Questions? All right. So this is how we test our coefficients, but we also want to go through and interpret our coefficients. Okay. So remember that what we're predicting with our model is not a probability, but it's a log odds, right? And so as a consequence, the coefficients that we're getting in our model represent the natural log of the odds ratio. Okay. Who can automatically intuit the natural logs of an odd ratio? Yeah, I can't. Right? It doesn't mean a whole lot to me, right? And so what we don't want to have is coefficients that don't mean anything. But what we can do is we can start to go through and exponentiate these to help them make a little bit more sense. So what we can do, if I want to get a strong interpretation of my literal interpretation of my coefficients, what I can do is I can exponentiate that. And what that means is I take my coefficient within my model, and I take that I take base E to that coefficient, and what this will end up doing is it gives me an odds ratio. Okay, so for example, my skiing example that we gave back here, right? My coefficient for difficulty is 1.01, right? And so what this means is that for every unit increase in difficulty, I'm seeing a 1.01 increase in the log odds of falling versus not falling. Okay? Who likes that? I don't like that. I don't know what that means, right? But what we can do is we can take that coefficient and we can take base E to that coefficient. We exponentiate this, and what we end up with is not a log odds, but an actual odds value, or odds ratio, okay? And so what this exponentiated value gives us is holding all other predictors constant at 0. This is giving us the odds of falling versus not falling for a unit increase in difficulty, right? So if I was looking at this coefficient, when I exponentiate it, I would say the odds of falling are 2.75 times that of not falling, are increased by 2.75 per unit increase in difficulty here, right? Or I could say a 1 unit increase in trail difficulty is associated with 175% increase in the odds of falling versus not falling. Okay. Now, the important thing to think about and sort of note with these models is that relative to our standard regression models, where if I want to see, if I have my coefficient is 3 for some predictor, that means like for every unit increase in my X, I get a 3 unit increase in Y, right? How would I determine how much a 2 unit increase in X would result in change in Y?
You just multiply them together.
I just multiply them together, right? So if my coefficient is 3 for a 1 unit increase, how many unit increase in Y would I expect with a 2 unit increase?
6.
6, right? And so it's pretty easy, straightforward. Our coefficients in logistic regression aren't that, they're exponential, right? And so what we see is we would multiply these. And so what we can sometimes see is, particularly with fine scales, odds ratios that aren't super large or don't seem super meaningful. But if we've got a very fine scale and we start multiplying 2.75 times 2.75 times 2.75 times 2.75, what happens to my odds ratio very, very quickly? they go through the roof, right? And so if we're going through and we're interpreting our odds ratios, right? If I have an odds ratio greater than 1, this indicates an increase in the likelihood of an outcome relative to my reference group. So if I have an odds ratio of 1.5, right, saying the likelihood of an event is 1.5 times that of a non-event given a unit increase in my predictor, right? Now, one of the things that you need to be careful when you're talking about and interpreting odds ratios, probability is a different thing. So you got to take probability out of the mix, because probability is talking about something different. You'll notice that as I'm going through, I'm talking about increases in likelihood. This is a better way to talk about this than saying probability, because probability is a different thing, as we talked about before, right? So here, if I've got an odds ratio greater than 1, telling me an increase in the likelihood of occurrence versus not occurrence for this group relative to a reference group, okay? So I could say, again, with an odds ratio of 1.5, I could say the likelihood of an event is 1.5 times that of a non-event given an increase in the predictor. Or I could say odds are increased by 50%. Ignacio, how did I get odds from an odds ratio of 1.5? How did I get odds ratio of an increase of 50%?
Just deduct a unit.
Yeah. So I've got a 50% increase in the odds of occurrence versus non-occurrence. Right. I could also see, Nick, I'm saying a 5-unit increase results in a 659% increase in the odds. Where did I get that?
You just rescaled it and multiply.
Yeah. So if I take, okay, there we go.
Is it 759, Josh?
Yeah. Oh, so your odds ratio would be 7.59, right? Why am I saying a 659% increase, Sean?
Oh, because you subtract 1.
Yeah. So if I take 1 point, so if my odds ratio for a unit increase is 1.5, okay, but these are multiplied, right? What do I need to do then, Sean, to get a 5-unit increase?
I'm sorry, I don't understand the question.
So if the odds ratio for a unit increase in X is associated with 1.5, how did you get to 759?
Oh, it's 1.5 to the 5th.
1.5 to the 5th power, right? So if my odds ratio is 1.5, that's for a 1-unit increase. I'm looking for a 5-unit increase. And with odds ratios, what we have to do is we have to multiply those odds ratios. So that's, if I want a 5-unit increase, that's 1.5 times 1.5 times 1.5 times 1.5 times 1.5, right? So if I take 1.5 and I take 1.5 to the 5th power, that gives me 7.59, right? And so my odds ratio is, so the odds of occurrence versus non-occurrence given a 5-unit, or the odds of occurrence is 7.5 times more likely than non-occurrence given a 5-unit increase, or I could subtract 1, call this a 659% increase in my odds. Okay. Same thing if I've got an odds ratio that's less than 1. This is indicating a decrease in the likelihood of some outcome. Okay. Here, if I've got an odds ratio of 0.8, it's saying the likelihood of an occurrence is 0.8 times that of non-occurrence given a unit increase in my predictor. Right. Alternatively, saying odds are decreased by 20%. How did I get that, Chris M?
It's 0.8 to the 5th power.
Okay, so but but this is just for 0.8, right? So it's just 0.8. So how did I go from 0.8 to 20% decrease?
It's 1 minus 10.
There we go. Right. So I'm just taking and flipping this around. So because oftentimes if I say the likelihood of something is 0.8 times that of non-event, that's kind of a weird way to say. I mean, I can talk about it, and that's perfectly fine, right? But the odds of something happening 0.8 times is kind of a weird way to say it. And so instead what I can do is I can just take 1 minus sort of that odds ratio and say, what I'm seeing here is a 20% decrease in the odds, right? Alternatively, if I look at 5-unit decrease, if I take 0.80 and I take that to the 5th power, that's going to give me 0.328. If I take that and I subtract that from 1, it's going to give me about a 67.2% decrease in the odds of something given a 5-unit change. Okay, so this is one of these things to be careful about when we're interpreting the practical impact of some of these odds, recognizing that these are taken to powers as opposed to just straight additive model here. Questions on interpretation? Okay, this is where that handout's going to be super helpful. Basically, that was me writing out an extended email to trying to help a previous class work through some of this stuff. And I was like, well, if I'm going to sort of let's hold on and keep that, turn that into a handout. So the biggest probably challenge of some of these models is working through and trying to make sure that you're on the right track in terms of what they mean, how we interpret them, so on and so forth. Okay, so do make sure that you go through and take a look at that, particularly if you are thinking about maybe jumping into this last set. Okay. Effect size for regression. There are different pseudo R-squared statistics. None of those are very good. Don't ever interpret those as percentage of variability counted for, because that's not how you interpret those. You'll see papers that try to do that, flag that, and say that's not a good thing. There's just really not a good sort of metric for these pseudo R-squared. So in terms of like absolute ability and utility of the project, looking at classification tables is probably a better way to kind of get a sense for utility there. In terms of individual predictors, odds ratio themselves are really good, are generally sort of a meaningful interpret metric of effect size, right? So CJ, if I say with the addition with this draft, I've got the odds ratio of sort of winning a championship versus not are it's associated with an odds ratio of 5, right? Is that good? Yeah. It's a 400% increase in the odds of me winning versus not winning. Now, my odds might not be great, but they're a lot better than they were, right? And so what we can see, or if I say wearing masks will result in, so the odds ratio of the association between wearing masks and likelihood and the probability of contracting an illness is associated with an odds ratio of 1.7, right? Tomorrow, how might I interpret that?
That wearing a mask will be 7% more helpful.
Yeah. You're getting the right idea, right? There's the odds of not catching versus catching is 70%. The likelihood is 70% increased of not catching versus catching, right? I like that. That seems pretty good to me, right? And so our odds ratios in and of themselves can be useful metrics. Now, if we wanted to take those odds ratios, and Tabachnik and Vidal talk about this, we can take an odds ratio and convert it into a D statistic. Ignacio, is this D statistic interpretable as we normally interpret D statistics?
I'm not sure, because you are talking about the odds ratio logarithm, the natural logarithm.
Yeah.
I don't think.
Yeah. What it can do is sort of like converting FX sizes to R's, because they just kind of make some sense, right? So you can convert, if you're wanting to get a sense for if this odds ratio is the relative size, you can transform that into a D using this very simple equation. Now, you need to think about if I've got a continuous variable with a very fine scale, right? A 1-unit increase in my predictor might not mean a whole lot, and so that D is probably going to be really small. But we can go through and start transforming these and sort of start talking about these as standardized effects, or generally roughly converting D's into eta squareds. So this is just kind of going back and forth between different metrics if it makes sense given your purposes. All right, going to finish with assumptions of our logistic models. Again, the nice thing about logistic models is that our assumptions are much, much more relaxed within these. So again, though, we still want to make sure that I have adequate specification, right? I want to make sure that the variables that need to be in there are in there, and those that aren't. Now, my model tends to be more powerful if my data is multivariate normal, but if it's not, that's fine. It's not a requirement for proper estimations here. What I do need to do, I need to make sure that my outcome isn't perfectly determined by any variable or set of variables. And this, again, Chris M., is where some of those small samples and those small cell sizes can start to become problematic just by chance. I can find, if I have small cells or small samples, that classification into one of my cells is completely 100% perfectly determined by a series of other variables, not because those variables have a lot of predictive value. It's just kind of how that fell out. And so what can happen is I can start to get my model crashing because I don't have adequate representation in my cells. So always important in screening to make sure if we have categorical predictors to make sure, look at representation, make sure we don't have very small cells, because that can start to cause problems. Expected frequencies. We need to have less than 20% cells having expected frequencies of sort of 5 or less. So your expected frequency of any individual cell needs to be greater than 1. So you can't have, or you shouldn't have, if we're going through and we're calculating expected frequencies, you should have no expected frequency of any of your cells that's less than 1, right? You should expect at least one person to fall in all of your cells. And general rule is saying not to have less than 20% of your cells not having an expected frequency less than 5. But again, this just starts to get into your sort of representation of sort of different cells and things like that. So this came into an issue for Shira's dissertation. This is my student who's on internship right now, getting big national comorbidity data with big 5,000 people in replication samples and things along those lines. But the problem is looking at different diagnostic status. If you start dividing those cells down, now all of a sudden as a sample of 5,000 people, the number of people observed who have some diagnosis sort of across men and women, things like that, you get like 3 people in the set. That starts to become problematic with stuff. So cell size is an important thing to be thinking about. Linear relation between your continuous predictors and your logit. Okay. So we don't have any assumption about linearity between my probability and my predictors. But when I go through and I create the natural log of that of the odds ratio, my logit, then I do need to, I am assuming I'm applying a linear model. I am assuming that I have a linear relation between my predictors and my outcome. What we do is we check this by looking at the interaction of a variable with its, of my continuous predictor with their natural log transform. If those interactions come up, it suggests I have a nonlinearity in my data that I might need to take a look at. And then this ends up being a specification issue. Ryan and I went through and took a look at some data and sort of found a violation there. And what he found was that a measure that he was working with had a very, very nonlinear association with likelihood of suicidal ideation or not, right? Again, it's a specification issue. You would want to go through it and make sure that that was being properly modeled. So something to go through and take a look at. Here, still not wanting weird outliers or multiclinearity between our data, between our sets, and then some independent responses. I want to make sure that CJ's answers are CJ's answers and not influenced by Chris's answers or Sean's answers. Given the current situation, CJ and Chris C are roommates, right? And so if we were going through and trying to do an independent sample of everybody on something, what we might expect, because those two live together, a dependency perhaps in terms of their whatever it is that we're measuring. We want to make sure that we don't have a nested structure to our data, but this is something that comes up more in terms of methods and things like that than something that we're doing a strong check for in our analyses. Okay. All right. That takes us through all of this. Let's take a break. And when we come back, we'll do a quick run through of one of these logistic models so we can just kind of see what those look like. And then we'll call it good. Okay. Awesome, guys. All right, you troopers. We'll see you in 10. All right. All right, folks. How are we feeling with the logistic models? We can kind of get kind of the basic idea of these. Okay. And this is one of these things where sort of thinking about and interpreting stuff will start to click a little bit more once you jump in and start working with these. Now, many of you probably won't, because you won't need to or won't elect to do this last set. But if you do, and as we're moving through, people have done pretty good. Just virtual open office hours, kind of whenever. If you're struggling with things, don't hesitate. Just shoot me an email, and I'm usually at this point able to jump on and sort of work you through. And having sort of shared screens is a nice sort of way to go through and do that. So if you're having struggles, let me know, and we'll get you squared away with things. Okay? Questions before we jump into a quick SPSS example. All right, so let's go through and open up with your data set here. And this is just a very simple data set. We're going to be working off of sort of this binary logistic worksheet here. And what we've got, this is data I hijacked from Narina, or Narina donated. What we're looking at is our outcome is a sentence in a homicide case. So life sentence or death sentence. So 0, 1. Okay. And our predictors here, we have a number of victim impact statements that was introduced by the prosecution. So victim impact statements are, this is the impact that this has had on us and our family and this and that and the other thing during sentencing, to sort of make a case for sort of maybe more stiffer, more serious sentence. What they've done is they've rated the depravity of the homicide, I guess, on a 0 to 100 scale, where 0 is not a depraved homicide and 100 is maybe sort of weird Dahmer stuff. I don't know what's going on, but like sort of 0 to 100 sort of depravity of the crime. And then we've got a categorical indicator here, where 0 is no impact statement or victim impact statement delivery. 1 is in private. 2 with question and answer between, say the jury and stuff. And 3 is open. I'm not exactly sure what all this stuff means because this is not my area, but we've got sort of a nominal variable that sort of captures different ways of going about and presenting this victim impact statement, right? So what we're interested in doing here is looking at whether or not these two, we'll treat these as continuous variables in this categorical variable, go through and predict whether or not the defendant was sentenced to life in prison or got the death penalty. Okay. All right. So what we're going to do first is, even though our logistic models don't have a great deal of, they were more relaxed in terms of the assumptions, still always a good idea to know what your data are doing and go through and just kind of take a look at your variables to see kind of what's going on. So what we're going to do, and I won't worry about pull down menu because you guys have done this time and time again. What we're going to do is we're going to look at well, I guess I will because I forgot stuff. Go down to look at our descriptives for our two variables that we're going to treat as categorical. So number of victim impact statements, and then this depravity score. I'm going to go through and we'll ask for skewer kurtosis just to see. Now, remember that my logistic model doesn't have assumptions about the distribution of my predictors, but my model still works. It's optimized if I have multivariate normal data, right? So it's always just a good idea to go through and take a look at things. So if I go through and take a look at my descriptives, right? Tomorrow, what am I seeing in terms of the distribution of these two variables?
They're ugly.
Yeah, they're both super ugly, right? But do we care? Nope, not all that much, right? Because we're using a model that doesn't depend on assuming that I have linear or normal distribution of my predictors. And so even if you're working with some type of model where you have predictors that have really, really weird and abusive distributions, if you've got an outcome that could be reasonably conceptualized as a yes-no type of response, these types of models are one way of going through and addressing that, right? Okay, so let's go through and take a look at what our distributions of these actually look like. Just going to use examine here. Okay, so here we've got someone who's still out here, right? I would probably still address this case, right? I mean, we've got 6 and then someone at 14. This starts to, that's an outlying value. 1, I would want to go through and check whether or not that's actually 14 and not supposed to be 4. Make sure that wasn't a miskey or something like that. I suspect it's a miskey. But if that was the actual case, still, even with our logistic models, we don't want to have weird stuff hanging out there. So I would go through and take a look at that, which the whole thing's skewed, but it's a lot better if that's not out there. In terms of my depravity score, it looks like people are kind of down here, just this normal run-of-the-mill murder, I guess. And then a few cases that are looking like, I don't know what happened, but it's looked to be bad, right? Now we could go through and we could smooth this, right? Because again, we still don't want to have outlying values, right? And how many people do we have in this set? 123. So we got a reasonable size set, but if I go through and I smooth, then I'm sort of worried about that maybe I'm losing some of the variability that I kind of want to see, right? So here, probably my biggest concern would be whether or not these are coming up as outlying values, but overall, I'm not too worried about the distribution, okay? What I am worried about is maybe, because I've got a categorical variable, I want to see whether or not I have adequate representation across my groups. So what I'm going to do is I'm going to go to Analyze. I'm going to go to Descriptive Statistics. I'm going to go down to Crosstabs. Okay? And then what I want to look at is in my columns, I'm going to look at my sentence, sort of death sentence or not, and then I'm going to look at VIS delivery. This is my other categorical variable, and then I'm just going to go through and I'm going to hit paste here, right? So what this categorical variable is going to do, or what this is going to do, is it's going to show me whether or not I have reasonable reasonable representation of my cells, right? So again, here, Chris M. So I've got some cells with some smaller values, right? But they all seem to be reasonably represented. The other thing I can do is I can go back to my descriptives, and I can go to my crosstabs, and I can ask for statistics here. And nope, that's not it. Cells, and I can ask SPSS to tell me the expected value of the cells, because remember, I want to make sure that my expected value for each one of my cells is at least 1, and that less than 50% or less than 20% of my cells have an expected value less than 5, right? So if I request this and then I hit OK, what I've got is my cell count and then my expected count, okay? Observed, expected, observed, expected. So Chris M., does it look like I'm okay in terms of coverage in terms of my individual cells here?
Yeah, everything's approximated to 1 and nothing is exceeding 5.
Yeah. So I'm doing okay with this, right? And so always want to go through and make sure, particularly if I'm looking for things that are quite rare, or if I'm sort of slicing and dicing my set into a lot of different categorical variables, if I have 5 different categorical predictors and a small sample or things that aren't super well represented, what can happen in 5-dimensional space? I can get very, very few males with conviction for assault who also have a graduate or a graduate degree or something like that, right? Like if we start slicing things up, it can start to get problematic. So always want to make sure that you've got reasonable representation here. Okay. So, other thing we might want to do is we want to go through and take a look at our frequencies of our sentencing, right? And so we've got reasonable representation here, right? So we don't have any sort of necessarily small cells in terms of our outcome. Reasonably balanced, not perfect, but we've got good representation here. Okay. Now, if you go through and you take a look at your handout, you'll notice that what I've done here is I've gone through and I've centered my 2 continuous variables, and then I've calculated the natural log transform of each one of those. Chris C., do you remember why we're doing this?
Why we center in general, or why we center for?
Well, why I might be interested in creating a log transform of my predictor variable.
It has something to do with the formula where you don't want 0 on the bottom, I think.
Yeah.
Like 1.
What I'm doing here is I'm working at linearity in my logit. Okay. What I want to know is whether or not my continuous outcomes have any nonlinearity relative to my logit function here. And so one way, and Tabachik and Fidel talk about this, I can do this by looking at the interaction between my continuous predictors and multiplied by the natural log of those predictors to get a sense of whether or not I have nonlinearities in those. It doesn't give me an exact test, but it just kind of tells me, do I have evidence of some nonlinearity going on with this stuff? So what I'm going to do is I'm going to compute, and this is just centering VIS and depravity scores, right? So I'm going to go through and I'm going to center those. And then if I go through and I analyze, look at my descriptives for my centered variables, they're nice and centered, right? And then what I'm going to do is I'm going to go through, because both of these variables, the raw variables, we go all the way back up here. I guess the depravity isn't 0, but it doesn't matter. So what I'm going to do is I'm going to create the natural log of both of these. And so to run this, and in my set, now I'm just going to have, here's my centered impact and the natural log of impact. Here's my centered depravity and the natural log of my depravity, right? And what I want to do is I'm going to put together a model that includes the interactions of the variable and its natural log to see if I have evidence of nonlinearity going on in my data. Okay. Now, the nice thing about logistic regression in SPSS, so if I go to Analyze, and I go to Regression, and then I go to Binary Logistic, and I select that. And Ignacio, what's my outcome?
One moment, please. No, I'm confused.
What's my dependent variable in this model?
Impact logarithm natural leap.
Well, for my overall model, I'm predicting sentence, right?
It's okay.
Sentence, yes, no. Okay. And so what I can do now, and Ignacio, what are my continuous predictors?
All the natural logarithms you just transform.
Okay. Yep. So I'm going to have my my natural logs in there, but I'm also going to have impact, depravity, right? And then I've got my delivery, Delivery is my categorical variable, right?
Yes.
Okay. And then what I'm going to do is I'm going to have my natural log of impact and my natural log of depravity. And now what do I need to do? What did I say I needed to do when I was looking at this?
Yeah, the interactions between the ln and...
Yep. Whoops. Yeah, I know. Whoops. Sorry about that. The natural logs don't go in there, right? So I've got my impact and my depravity score here. And as Sean said, what we need to do is we need to include the interactions, right? Now, normally with Sean, with our standard regression models, what would I need to do to create those interaction terms?
You could do it by calculating it in SPSS, or I think you can highlight both of them and then use that A times.
Yeah,
right?
yeah, this is nice. So if I hit impact, and then I hold down Shift, and then I hit the natural log of impact.
Control, right?
Or Control. There we go. So if I hit impact and the natural log of impact, and I get both of those, and I hit this A times B, it creates that interaction for me, right? And then if I hit depravity and the natural log of depravity, move that in, and now I've got my interactions there. Okay. So here I'm going to kick out delivery here. So I've got impact, depravity, and then these interactions. And these interactions are what's going to tell me whether or not I have weird nonlinearities in my data. Okay. And then the last variable I have is my VIS delivery. And Sean, we'll just keep with you. What's going on with VIS delivery? What's happening here?
It's categorical.
It's categorical, right? And so normally, how would we, if we were running a regression, how would we deal with that?
Set it up as dummies.
Set it up as dummies. Again, the nice thing about this logistic model is I can go up and I can choose categorical and just tell SPSS that VIS delivery is categorical. And then what I can do is I can say, how does it want me to set this up? We'll leave this as an indicator. But then what I need to do is I need to go through and need to tell it which one's the reference group, right? Now, if I pull back in this, I'm probably going to want none, the first group, to be the reference group, just because none seems like a good reference group versus any of the others. So in the module, if I go through and I say I want the first category to be the reference group, and then make sure I hit change. So it's going to say, okay, VIS is my categorical variable, indicator, and the first group is my reference group. Then I'm good to go. Okay. If I go to options, I can say that I want confidence intervals for my exponentiated coefficient. And that'll be good enough here. And hit continue. Okay. All right, now I'm going to go ahead and hit paste. So what I've got here now is my categorical model. And if I go through and I run this, all right, here's my model. But Chris C., do I care about all this stuff? What am I doing this? What am I running this model for?
Just to test the linearity, right?
Test the linearity, right? So if I just go down to looking at this table that's variables in the equation, and I look at my interactions here, am I seeing evidence of non-zero interaction effects?
No.
No, right? So what I can say is, it looks like based on these data that I don't have non-linearities in these data that I need to worry about. It looks like modeling these as linear functions against my logit is going to be fine, and so I'm good to go with this. Okay. So there's other stuff that we would do in sort of standard screening just to kind of like take a look at our models, at just kind of what's going on. Want to look at univariate outliers and things along those lines, but you guys know how to do all that and sort of take a look at things. What I'm going to do is I'm actually going to go through and actually estimate the model that I want to look at. So I'm going to go up and I'm going to analyze, and I'm going to go to regression, back to binary logistic. Okay. And so sentence, that's still my outcome. And I'm going to keep impact, depravity, get rid of these interactions. I don't need those. Okay. So I've just got my 3 predictors: centered impact, centered depravity, and then my VIS delivery, which is my categorical variable. I'm using the first category as my reference group for that, which is good. And so I'm just going to go ahead and I'm going to hit paste here. Going to run my model. All right, and go down and take a look. So here we see, in terms of my model that I'm wanting to take a look at, looks like I have 123 cases in my model, which is good because I have 123 cases in my data. Makes sense to me, right? Always important. Remember that the interpretation of your odds ratios, you always need to know what your reference group is. Here, it's telling me that life is coded as 0, death is coded as 1. Looks like with the way I've got this coded, death sentence is my criterion, life sentence is the reference group. Looking at my categorical variable codings, this is important too. It looks like, again, Chris M., who's my reference group based on this here?
It is private VIS delivery.
What's that now?
No VIS delivery.
No VIS delivery, right? And so my first indicator is private versus none. My second indicator is Q&A versus none. My third is open versus none. Okay. Again, always essential that you know which how these are categorized. Okay. If you go down to your first classification table, this is just saying if I have no variables in the model, what does my model do in terms of classifying? Okay. And here, CJ, what's gone on in terms of my classification table of my model with no predictors?
The percentage correct for death is very high and very low for life.
Yeah, right. So I've got so 100% of my people who have who had received the death penalty got the death penalty. What did my model predict everybody got?
Did it predict
death? Yeah,
death.
Right. And why did it predict death?
Because we made life the reference.
Kind of on the right track. Anybody have a guess for why my model, when the absence of predictors, just guessed that everybody got the death penalty?
Death was higher.
Death was higher. Death was the more frequent thing, right? And so in the absence, even if it's 51 versus 49, just guessing everybody got the death penalty is better than guessing the opposite, right? And so what it's done is, without any predictors, it just guessed the most frequent category for everybody. Okay. So this is just looking at the model and the predicted value when we don't have any predictors. Okay. But then when we go down through, and here's our model, this is our test of our actual model. This is our omnibus test. This is our chi-squared test. This is testing the -2 log likelihood of my model against the -2 log likelihood of the model with no predictors. And so the difference with the inclusion of my 5 predictors is 21.05 against a chi-square degree of freedom 5 test. And CJ, what is this telling me?
That you reached benchmarks for significance.
Yeah, it's telling me that I have pretty good evidence that my model with my 5 predictors is providing better fit to these data than the model without any predictors at all, right? This is my omnibus test right here, okay? So I've got my -2 log likelihood for my full model. This is the difference between my -2 log likelihood for my full model and the model without any predictors. These are your R-squared statistics, which we don't worry too much about. And here we get our classification table. Nick, what are we seeing in this classification table relative to sort of what we had before?
Our percentage correct in terms of predicted versus observed is a little bit higher.
Yeah, right. Basically, what this is saying is functionally a model with predictors is better than just guessing the mean, right? And so it's 64% accurate overall. That's still not great, but it's better than what it was, right? At least in terms of a statistical sense, okay? Then we get down here to the bottom. This is our equations. These are our individual predictors. Again, Siley, what are we seeing in terms of, what are you seeing come up as sort of evidence for an effect here?
The VIS delivery?
Yep, VIS delivery. And so this is a test of the categorical variable as a whole, right? And so we have evidence that VIS delivery as a whole is sort of providing some predictive value for the model. Here we're seeing individual, our individual dummies. Which one of these is giving us evidence as showing the greatest differentiation here?
VIS delivery 1 and VIS delivery 2?
Well, is one is doing good. What's 2 doing?
It's the opposite.
Yeah. Well, remember if we go up here, right? Remember that in our table here, here we go, right? So VIF1 is giving us private versus nothing. 2 is Q&A versus nothing. 3 is open versus nothing, right? So VIS delivery 1 is going to be private versus none at all. And if we take a look at this, we see we have some evidence going on here. Here is our coefficient, but what SPSS does is this exponentiates it for us. And so we see that this is associated with an odds ratio of 0.26. Nick, what does this say about the difference in delivering the VIS private versus none at all in terms of our odds ratio? Does that increase or decrease the likelihood of a death sentence?
That would decrease the likelihood of
Right.
a death sentence.
So what this odds ratio is telling us is the odds of death versus life for individuals who give VIS in private is about 0.26 times that of the odds of death versus life for none at all, right? Suggesting that if I go through and I deliver this in private, it actually decreases the odds of a death sentence for this relative to not doing anything at all, right? And if I went through and I took 0.261 and I subtract that from 1, so it'll be basically about a 74% decrease in the odds of death versus life for those individuals who present in private versus those who don't present anything at all. Okay, Nick, what else are we seeing in terms of things that are popping up here?
We see
Depravity score, right? And can you take a stab at that odds ratio there?
So it's more likely that someone would get the death penalty the greater the depravity is rated, and that would be just over just over like coin flip 50-50 chance of that being the case.
Right. So it's very, very close. But what's the scale of that depravity score?
It's 0 to 100.
Yeah, right. It's a lot, right? So if I look at depravity, it goes from 2 to 73 with a standard deviation of 8.87, right? So if I take 1.106 times 8.87, I take that, if I take 1.106 to 8.87, take it to that power, I get a exponentiated odds coefficient of 2.44, right? So what I can say is that if I'm just looking at this, I'm saying a 1 unit increase in depravity score results in about an 11% increase in the odds of death versus life, right? But if I exponentiate this out, if I look at standard deviation increase, I'm getting about 144% increase in the odds of death versus life for a standard deviation unit increase in this. And so it starts to make it sort of more, you get more interpretive value with that. Okay. All right. So we've gone through this pretty quick, and this is our last class. I'm not going to hold you over to go through and move through some more of this stuff. What I can do is I think I've got a screencast of working through the handouts and stuff like that, kind of talking about these models a little bit. I can go through and post that if anybody's interested or sort of wanting to learn a little bit more of how we go through and interpret these from a practical standpoint. Again, for most of you, I expect this mediation set is going to be the last thing we have to worry about. But if you are thinking about sort of jumping on this last logistics set, we'll have it due sometime. I don't know. But if you're interested in doing that, if you're right on the cusp, let me know, and we'll just make sure to get your stuff scored so that we can get it back to you, so that you have all that, and so we can kind of know kind of where you were at or what you would be shooting for in terms of making a difference in terms of grade stuff. Okay. All right. Questions on any of this stuff, where we're going, anything along those lines? All right. Hey, this has been a fantastic semester. We're not quite done yet. We still have a couple things to turn in. But let me know if you run into difficulties or hiccups with anything. Again, we'll shoot for midnight on Monday of finals to get that last set turned in. Again, hopefully that won't be too burdensome. But again, keep me posted with stuff. But otherwise, it's been a bummer to do this via Zoom for the last half of the semester. I much prefer to be there with you all in person. But I think we kind of made the best of it. I feel like this class lends itself maybe better to this format than other stuff. But we did the best that we could with it. So awesome. All right, you guys have been champions. Again, thank you so much. If you have questions, let me know. Otherwise, good luck closing things out for your semester. It's sort of been a weird first year. So glad you're locked into a doctoral program that you can't leave. All right, cool. Well, yeah, let me know if anything comes up. What's up?
Can I talk to you after?
Yes. Anybody else? All right, folks. We'll see you. You can sign off. Have a good evening. And yeah, we'll catch up with you at some point. All right. Thank you. I got Chris C is giving me applause. Thank you, Chris C.
I thought other people would join in. But
You're just
We're just doing a silent clap.
silent clap, right? CJ's got snaps, right? All right. Cool.
Thanks, Josh.
Yep. All right. Hey, thanks you guys. Good luck closing out your semesters.